Today I want to present about animal experiments and how to design our reinforcement learning experiments based on these. So what is the motivation for doing such a thing? Well, to me, the goal of AI is to achieve animal level intelligence in our computational agents. So if we design our environments such that they take into account the challenges animals have to do, then if our computational agents can solve these environments, they are in fact solving the issues that animals have to overcome. So for my talk, I'm going to give an example of an animal experiment and then show how I transform it into a computational environment as an example, and show what kind of insights we can gain from just that process alone. So the experiment I want to be talking about involves macaques, which are a type of monkey. And in this experiment, there are two macaques, and they're sat in front of a screen. And one used its hands to select on the screen its actions, whether it was choosing an option or whether it was pressing a button. And the other one used only its eyes. So it would look at the button it wanted to press or look at the option it wanted to select. Yes?
Was it constrained to only use hands or eyes, or did they?
Yeah, only one or the other. Okay. So one monkey was trained to do just the eyes, one monkey was trained to use only the hands. And the only reason they did this was to show that it didn't really make a difference which way you did it. They just wanted to show that. Because from the results, the monkeys scored pretty similarly for each. Oops. So there was a total of thousands. So these monkeys did these things called trials. They're a little matching task, and I will describe the trial in depth. But first, I just wanted to say that these monkeys did like 106,000 trials together. Each did around 50,000 trials. That is a lot of trials. But each of these trials are like 3 seconds long, a few seconds long. And we're going to walk through a single trial right now. Yes?
Did they have pre-training on using the screen?
So did they have pre-training? No, they kind of learned fresh to the interface. But then the authors give results of how they performed through time. Yeah. So the trial starts with the screen showing this white dot, and so the monkey using its finger would touch the white dot for around 250 milliseconds, and the one using its eyes would focus on that white dot for 250 milliseconds. And then that would prompt the reference image to pop up. So what is the reference image composed of? This is an actual reference image used. It's composed of an object. So in this case, it's a zebra. And that object is a 3D model, actually. And what they do is they rotate it randomly and then they also translate it randomly, so it's somewhere on the screen. And they also scale it randomly. And the background is random. So the background could be mountains, it could be a road, it could be anything. And so and this only shows for 100 milliseconds, so it's a quick flash. And then immediately after that, the monkey is shown two objects in a neutral view. So the zebra will always pop up like that, the dog will always pop up like that. And the monkey that's pointing has to choose the one of the object that it thinks it just saw in that reference image. And the one that is using only its eyes has to focus on the proper object for 700 milliseconds to indicate that it's selecting that one. And they have 1.5 seconds to do the selection. Otherwise, this trial ends, and it might show up later. But they only have 1.5 seconds. And after they select, then comes the reward part, and either the monkey's rewarded if it chose the correct object, and 4 juice squirts get squirted into its mouth through the straw. Otherwise, it gets a timeout. And in that case, the monkey has to wait 1.5 seconds to 2 seconds. So I just wanted to go into, and so that would be the end of the trial. So I just wanted to go in depth into the trial to see, show you what these monkeys go through. And this is just the overall trial. There's the start screen, which is 250 milliseconds, then the reference object, reference image with the object in it. The monkey has to identify it, there's a reward, and then the next trial can start with the start screen again. So these can be back to back, actually. And they were done back to back. Oh, okay, sorry. So the question I want to ask is, how do you convert this into a computational environment? Well, we can, as an approximation, we can consider each screen to be an observation. And then we have to approximate these within these observations, as we'll see. So we already have this idea within reinforcement learning, the idea of partial observability. So the environment just gives you observations. So for us, it'll be the screens and actions. The monkeys take actions left or right to choose this decision. Yeah. So here's how this is one iteration. I mean, this is one approximation of the experiment. So for the start screen, you just show the start screen as the observation. Then the reference image is just shown as it is. But for when the monkey is deciding which image to choose, there's many ways you can do this. And it actually depends on the behavior of the actual monkey during this stage. For example, you can alternate between the two objects and then eventually settle on the final object. That's assuming that the monkey is looking left and right, which it does in the beginning of the trials. It actually does look left and right.
This is a computational thing?
Yes.
So there's no monkey here?
No, there's no monkey here. So I'm basing it off the monkey experiment, though, the data they collected. So, each of these elements would be a screen. So I just want to replicate what the monkey's actually observing in its environment.
Well, earlier you said they actually see both animals.
Yeah.
But now you're going a next step. I'm trying to understand what the next step is.
Yes.
So the next step is your formulation of the problem, and you're formulating it in a certain way. So tell us, so how are you formulating it?
Oh, okay. I see what you're saying. So you could actually, for this step, show the two options.
Yeah.
Yes, you could just show them.
Instead.
So I did actually take an extra jump. So each of these images, there's a detail about these images that were shown. Each of them are sized in such a way that only that image is clear in the visual field of the monkey. So when the monkey looks at one image, it can't really see the other image. And when the monkey looks at the other image, it can't really see. They can't see both of them at the same time.
So this is
because the screen is at that distance.
So you're actually trying to capture the saccade that happens with
Yes. But you don't, so this is just one way of doing it, but this is just a gross approximation. In fact, the monkeys initially would look left and right, but eventually in later trials, they didn't even have to look left and right. They would immediately go toward the correct answer as opposed to looking left and right.
And that was with the order of the images fixed, so it wasn't learning to go left, it was learning to go towards the correct image?
Sorry, can you say that again?
The order was properly randomized, so it wasn't learning that it should look to the left, it was learning to go to the
Yeah,
right.
all these objects, the position of the right answer was randomized. I am not trying to replicate the experiment exactly. What I am trying to do is incorporate the challenges that can come. And I consider this a challenge when you see the wrong answer and the right answer, just because it adds extra information in the observation that like the dog.
So I just want to understand what you're doing.
Yeah.
So you're saying you see four things there, but there should be.
Oh, I see.
What's happening?
So yeah, so it would. I am not saying that all four of these show up at the same time. One of these would show up at maybe like 1/4 of 1,500 times for 1/4 of this time interval.
One of the two
Yeah.
will be shown.
Yeah, so this is,
Isn't it random?
isn't it random?
Chosen at random. The order?
Oh, the order of showing?
Yeah.
Yeah, you can make it, so the order of where, okay, I see what you're saying. So I'm assuming that they're underlying this environment, the two options are shown side by side, and that is random. But deterministically, it might look left and then right, left and right, this computational agent.
So in the experimental framework, you have two pictures essentially chosen
Yeah.
randomly, and you look left and right and
Yeah.
left and right
Yeah.
always?
Yeah.
Although that shows 3 times looking at the zebra. Is it choosing where to look?
Is it choosing? Are there actions?
No, I am not talking about actions right now.
So how do you?
These are just the observations it sees.
First one.
That would be given by the environment.
How does the environment pick?
It just chooses the first one. It just chooses the first
It always
option.
shows the one that's on the left.
Yeah.
Of the randomly generated
Yes.
pair.
Yep.
And then it always shows the one that's on the right.
Yes.
And then
It shows the one on the left, and then can select it by just keeping at it, like keeping its.
So there are actions.
Sorry, I thought we were talking in terms of the environment. So okay, let me just clear this up. So each of these, okay. So how this is chosen, I didn't want to actually get into how this is chosen very specifically because you can do this in however way you feel is appropriate. What should be maintained, like you can even forget about the other object. You can just choose either the right answer all the way.
Who's you?
So the designer of the environment. So we're designing an environment right now. And you can either choose the right answer, so the zebra along the entire 1,500 time interval to be shown at every time step, or you can choose the dog to be shown at every time step for that entire interval, just to represent that these are the observations that agent is seeing, and then the reward would be determined on whether those correspond to each other, whether the zebra was picked in the end or the dog.
So you have to talk about actions eventually.
Yeah,
Because you're going to get the reward depending on whether the agent got it right.
the agent isn't choosing the action. The designer is saying, I'm going to go left, right, left, and then show the correct answer.
so yeah, that would be the prediction task where okay, so yeah, we can talk in terms of action as well. So say within that 1,500 time steps, the agent does determine whether it should look left or right, and it just keeps choosing that, and that's how the observations are shown. And then and if it does stay on the correct answer for 700 time steps, as like was done in the monkey experiment, then it will see the reward pop up, which can also be approximated how you like. And in this case, I did the 4 juice squirts as 4 up and down rewards in the time steps. But if they got it wrong, they didn't choose the right answer, there would be no reward. And then after that, the start screen would show up again. Yeah.
So to clarify, are you showing a prediction task? Just pick.
I'm showing a control test.
You're showing
Yeah.
a control task.
Yeah. And so the actions are only the left and right in there.
Okay, so the agent's stream of interaction with the environment
Yeah.
is observation, action, reward, observation, action, reward,
Yeah.
observation, action, reward. Each observation is a picture of some form. What are the actions?
The actions are just left and right.
And no?
Yeah.
Because you said
Well, I mean, if the agent does left or right on those observations, it won't. You could
literally in
do.
the computational
Yeah.
framework, is there a back and forth interaction between the simulated agent and the environment? And if so, what actions are taken on or are they available to you?
I only consider left and right
Okay.
because
So this is
Yeah.
a particular sample where it shows left and you showed the zebra in this case, and then it chose right and showed the dog, and then it chose left and left.
Yeah.
Like the trajectory we're looking at here.
Yeah.
And then is that reward that's for 15, I assume that's reward?
Yeah, this green thing. Yeah.
That's actually at the same time as it's choosing these images?
This is after.
Okay.
Yeah, this is after.
We might need a diagram.
Okay, continue. Yeah.
One more. When do actions have any consequence on the subsequent observation?
Only in this time interval.
Okay, so for each of those dots, there's 4 actions.
Those aren't 4 actions. There could be many actions within that time interval.
Those are 4 time steps where the actions chosen were left, right, left.
Yeah. Yeah.
Okay.
And what's the granularity of the time step?
Well, just a time step. So you. So.
In terms of
So in this case, there's 1,500 time steps.
you're saying each time step is 1 millisecond.
Yes, and that's also a strange approximation because the macaque might not see 1,000 frames per second, but it could. But you can change that just by dividing it. Probably.
So
Yeah.
is the artificial agent actually picking an action at the frame rate, or is it picking an action?
It would be at the frame rate.
Okay.
Yeah.
All right. So there could be 1,500 frames.
Yeah, I should mention, the milliseconds were converted just into time steps, just as a simple conversion. Yeah.
And then you give it a reward if it takes the correct action for 700 time steps in a row.
Yeah. Exactly.
Maybe one last one. What's the duration of the reward?
It's still 1,500 time steps to 2,000 time steps. I said that because that's what they said. But yeah, you would just split this across. Whatever you decide to be the reward structure.
So on the environment side, it will take, after that action selection period, it will say, if the agent was looking in the right place for 700 consecutive time steps, then you get a reward that lasts for
Yes.
500.
That however long.
Okay.
Yeah, exactly. All right, is that clear? Oh, cool. No, I mean, I didn't realize it was that unclear, but thank you. So what are some important aspects of this? Well, there's of this environment. Well, there's the visual challenge, just because of the images. Being able to recognize the invariant features of the objects as they're rotated and moved around in space. So that's just an aspect of this environment. And I wanted to just touch on, because there's other animal experiments like this. There's also one done on humans where they showed the image, then they showed some noise, and then they asked the human to say what it just saw. And so you can also construct an environment in a similar way just by adding that noise feature. So that would also be a visual challenge in my mind. And I think that's an interesting visual challenge because depending on how much noise you show, depending on how long you show the image, the human won't actually see anything. So it's just, you have to take that into account. And then there's the temporal challenge because, it is strange. It's like this huge time span where actions don't mean much. And then there's another one where the reward is given over a long time, a lot of time steps. So that is the temporal challenge. And I feel like you can abstract away all those visual challenges and just get the temporal challenge by itself. And so that would be the start screen, this bit vector, and this would be the object that it saw. And then again, you choose actions, and depending on what actions you choose, you see the wrong object or the right object, which is equal to the reference object. Eventually you get a reward, or you don't over the reward period. And so that's just a very long period. And then it would start again. So really, it can actually look like this. And so then it becomes like, what should the agent, so let's say you want to turn this into a prediction task. You have, so that would be taking away all the actions and then deciding a behavior policy. Say you wanted to predict something about this. Well, maybe you can predict different horizons or different prediction questions. Because to me, it's not too clear about what's the correct prediction horizon for this task. And yeah, and so if you predict many different horizons, you'll have features that are great for the horizons it can predict. So, and in my opinion, this temporal challenge, I think it's very challenging. So I kind of like it. Oh, okay, and so I realized that a lot of this has to do with the state update in this experiment, in the sense that you're given all these observations, and then you should let them contribute to your state such that you keep the important information. And so it becomes a question of like how you should memorize and what you should keep, and so that you can properly predict the value, and then somehow that value can be used to take actions on the environment. So I thought that aspect of this experiment was interesting. Yeah. And yeah, another thing I like about this experiment is that they have aspects that are kind of easy for humans and relatively easy for the macaques. They scored over time, they actually scored pretty close to human level of object recognition. So this is just something that might be actually hard for computers to do, though. And so it'll be a nice challenge to overcome, just because it comes so naturally to us. Yes? Is it questions? Yeah, sure.
So I haven't read about this experiment before, but I imagine they had a variety of objects they were choosing from.
Yeah.
So the disadvantage of the bit encoding is it encodes the sameness, and unless you have a very large bit vector, it's the same task every single time, really. Like the left or right might be flipped, but it's always just matching the same bit.
Yeah, that's actually a mistake. So the thing is, yeah, that bit vector could be much larger to account for different objects, and then you would see, you wouldn't want it to be the same task every time. So you would have a bit for each object. Yeah, there were 24 objects in the original experiment.
Done any modeling? Do you have an idea of a computational model that could actually do this?
A computational model? Oh, that can actually solve this?
Yeah.
No, that's what I'm going to explore now. Yeah.
Because I think one of the features of the macaque experiments are that it can do the generalization to same without having seen, like, you'll show it a brand new object it's never seen before, and it will, once it's learned to recognize same, it will recognize that concept of same. But I know these are used for understanding that conceptual level. And I'm really curious if anybody has any idea about how to capture that transfer of sameness to a totally random bit in a computational framework.
Yeah, that's definitely the key thing. At least that's what I also thought. Like, how can you compare things through time and consider them same? Yeah, I think that's interesting.
Sorry, what was the problem with predicting different time horizons?
Oh, I was just saying, like, if you wanted to turn this into a prediction task, so then you would choose a behavior policy, because I mean, I don't know if there's a time horizon that sticks out to you that seems like most important to predict, but like I was just thinking, like, you could just predict a bunch of different time horizons and see which one works, like which one you can actually predict.
The translation of the time horizon and the time steps from real experiments to the reinforcement learning framework is a super challenging question. And a lot of our kind of default structures don't lend themselves to temporally extended signals. So, like, we did an ancient experiment on modeling this mediated association with predictive representations, and that was the first problem we ran into, is that time signals last for multiple time steps, and previously we'd only been doing visuals, so it's a really interesting area.
Yeah. Well, yeah, I was just going to say, also with the sameness, just because I transform them into a bit vector, it might not be the best way, because maybe that sameness measure would need that the bits to be different in order to classify them.
Maybe it needs a feature representation that's picture
Yeah,
in order
yeah.
to do the generalization, but
Yeah.
maybe not.
Yeah, maybe.
Yeah, relating to what Anna said, so something about how it's difficult to translate these time into time steps, and now when you have actions that last across time steps, then your learning mechanisms kind of get avy. So related to that, so these, for the macaque experiments, I'm assuming that some of these time scales of like showing it for 100 milliseconds and squirting the juice for 250 milliseconds or things like these are chosen based on, I guess, some studies on, okay, how much the fixation times are and how long it takes to like focus and things like that. So that is why the original experiments chose those time steps. So is there a particular reason why we might want to stick to those very lengths of time here?
No, I thought, I didn't think there was a particular reason, but I just liked the ratios preserved of how long they were, just to stay accurate, at least to the ratios. I didn't really care about how many time steps specifically. Just because that's what macaques can do. At least that's what they showed they can do. So just by sticking to those ratios, at least you have preserved some of that. There are probably other experiments that change that.
It seems like from an exploration standpoint, this is a really tricky problem, because even if you have a state that captures all the important stuff, like how many actions you've taken in the past 700 time steps, but how many consecutive actions you've taken in the last 700 time steps, you still have to be really strict about like maintaining that consistency over a long period of time. And I was just wondering, excuse me, if you had thought about how a computer would do that.
So I did think about the exploration part, because before I didn't see that. Actually, the macaques do explore, because they don't really know the task exactly, because no one communicated it to them. But yeah, so then they have to explore. So I don't know. I didn't really think that hard about it though. I just know there's definitely an exploration component, and I'm not sure exactly what you were trying to get at, but I think definitely some of these challenges they do on macaques and rats and even humans lend itself to like these interesting exploration problems that actually happen in animal worlds, in real worlds. Sorry.
I was just thinking, in some sense, the experiment on the macaque isn't the thing that led to the natural intelligence in the animal. So I was just wondering, like, does that mean that this is like a good, like, is it good to approximate this kind of problem to develop computationally intelligent agents? Because in some sense, the macaque experiment was designed by someone, and like in the wild, the macaque wouldn't be, it wouldn't have this kind of specific task, right?
There are parallels in the natural world, and there's some, in comparative cognition, you'll find some field studies of its related experiments. And like this one is kind of getting at the same different idea that exists in the wild. Sorry.
No, what Anna said. So she was saying that like the same difference. So the same difference. From what you're saying, I think it's where animals can recognize if it's the same object they've seen before or a different object they've seen before. So macaques can do this. This is just a formal lab experiment that you actually have measurements, you actually have real data about it, and you can actually prove that they have that ability. So animals actually do have that ability, and so that's why I like these environments, because even though it's not a wild example, it is one that they have. It is something they can do. And humans, there were human subjects in this as well, and humans can do it too. So
There's cool follow-up experiments too, with like there's recognizing the same object, and then there's recognizing that you saw the same object in the two time steps or for 2 periods in a row, and so can you choose the thing that is the same, a different object but the same? Like there's layers on layers of metacognition on this kind of train of research. That's really interesting. And as far as I know, it can't be represented computationally yet, so cool research.
All right. I guess one of the final questions.
So, I understand the macaque experiments were mostly maybe, but then in the computational imaging, you've made some fairly particular choices, like having time steps be really, really fine, and allowing actions to have some effect at some points and not at others, right? So like the macaque actually has to look at that dot before starting the next one. And presumably the macaque's eye can sort of wander a bit as it's fixating on the appropriate object. So I guess all of this is to say, which attributes of the macaque experiment are the most pressing to be modeled, right? So you could try and model, oh, saccades take 30 milliseconds, right? Or you could say, oh, I want to see if I can do this with a tile coding on a webcam, right? Where decisions are made every 30 milliseconds. And maybe there's some traces of the tile codes for a little bit of statement reading, right? So you could go from the macaque experiment to a computational experiment in many different ways, as you described.
Yeah.
And so which questions are the most pressing?
Okay, yeah, so I was biased in like, I like the time expansion problem aspect of it, so I did focus on integrating that to a high degree. Yeah, and these transitions are very fast, like they're like within the milliseconds. So you're right, so it's, and then there's time between the saccades and everything, so maybe the maybe the macaque isn't seeing as much like per time step, and it's not, and there's just very few time steps which actually matter to the macaque. I do think that is like a important thing to wonder about. I mean, not wonder about, like to investigate, like how much of the eye movements should you incorporate, even like how the images are presented. You can go there, but that's actually a different level. So we're just talking about the time aspect right now.
There's similar structures
Yeah.
too, where they have like button presses, so the discreteness is replicated in real animal experiments. Replicating saccades is conceiving continuous space, and we just don't do computer vision that way, so I don't know. That's a hard one, I think.
Something nice about this is that they kind of force so the saccades only happen here. They kind of forced the macaques to keep their attention on the center of that image, actually, by like, if they deviated too far, I think the trial was nullified or it was stopped. I'm not sure, actually. I don't remember. But they tried forcing the macaque to always be looking at the screen. If there was too much deviation within the trial, I think they discarded it. But they tried making sure the macaques, as much as possible, stayed focused. But the saccades happened in this. All right.
Okay, thank you very much.